I think we can start. So now we're going to learn how to do bit twiddling like the best C programmer at the same time as we keep algebraic data types. So please, Thais Boudon.
Thank you. I'm going to talk about bit twiddling made legal as in clever memory tricks and low-level memory optimizations like bit twiddling made legal as in nicely abstracted way and correct. So the link here is a link to an online demo, so you may go online and play with Rebit, which is our compiler. So first, what we're dealing with, what we're targeting is basically any program that needs some sort of performance or low memory usage, and that also uses some sort of inductive data structure. So inductive data structures, they're used basically everywhere. They include various kinds of trees, like red-black trees, shown here. And there are two really neat language features to have when dealing with them, which are algebraic data types and pattern matching. So algebraic data types, they're types that combine sum and product types. For instance, here we're going to model red-black trees with two sum types, which are color and RBT, which each have two possible tags. Inside the node tag of the red-black tree type, we also have a product type that aggregates four fields together. So with ADTs, we can easily and intuitively model red-black trees because a red-black tree is either empty or a root node, which contains a color which is either red or black, a 64-bit wide integer value, as well as left and right subtrees. ADTs are especially useful when we combine them with pattern matching, that is when we write functions that inspect the shape of data to express control flow. For instance, here, if we count the total number of nodes in a red-black tree, it's obviously 0 for empty, and it's 1 plus the cardinals of each subtree for the node case. So this is concise, this is also safe, because we get static guarantees that come with ADTs. Here it's quite immediate that both cases are dealt with, node and empty, and that when we talk about T1 or T2 in the right-hand sides of each pattern, they actually exist, and we know that they're of type RBT thanks to the very structured ADT we have there. So pattern matching is especially interesting for operations that inspect nested structures like this rather complex rebalancing operations on red-black trees. It's relatively concise and readable, at least when compared to patternless alternatives, because we follow the structure of the data to express control flow. So when we're dealing with this kind of data structure, any kind of tree, basically, we most definitely want to use a language with these features, with ADTs pattern matching. Now that we have established that they're quite useful language tools to have, the next question is, what about the performance cost of these nice abstractions? And the answer is that it mostly depends on the memory layout that we use to represent data. The problem is that compilers for languages with ADTs and pattern matching, they typically assume a fixed and somewhat uniform memory layout that you can't fiddle with. So, for example, it might be a naive representation like this one. So here we can see, using a kind of graphical language I'll keep using for the rest of this talk, that empty maps to the null pointer, and that node is always hidden behind a layer of interaction behind a pointer to a block or struct in which we take up a whole 64-bit wide word just for some assorted metadata for the header, then another one just for the color bit, and finally we get the rest of our data in the three remaining fields. So why is this a problem? It's a problem because in the real world, inductive data structures are also used in performance-critical programs, like the Linux kernel, which uses red-black trees internally. In Linux, red-black trees follow a memory layout that is optimized by hand for performance and especially for space, as shown there. So if we compare it to the previous naive layouts, we can see that we're storing more information in less space because we have a parent pointer squeezed in as well. So it makes use of an optimization which is known as bit stealing, because since red-black tree pointers are word aligned, the lowest significant bit is always going to be 0. And here we're using this free bit at the end of the pointer to store the color, which is just 1 bit, so it fits in there, and it prevents us from allocating a whole extra word or half word just for a Boolean. And the downside of this nice, custom, finely tuned layout is that it requires control over quite low-level details to write. So it's only available through languages like C, and accordingly, in the Linux kernel, data types are written using C structs, and the whole data manipulation code is polluted by the clever tricks we decided to use in the layout. So if we're looking at simple parent accessor, it requires masking off the lowest bit of the pointer, then dereferencing it, and then we also get a pointer cast thrown in for good measure. So if we look at the rebalancing operation, it's even worse. It's especially clumsy and painful to write and maintain because for each match case of the pattern matching we saw earlier, we need 5 to 10 lines of code in C. So to add to the problem, we completely lose the static guarantees that come with ADTs because whether the low-level data type here properly models what the user actually had in mind, in that case, red-black trees, and whether the data manipulation code is correct, everything is all left up to the user. So our main goal in this work is to combine hand-tuned, arbitrary low-level memory layouts with ADTs and pattern matching, which are nice abstractions. So we achieve this by providing a specification language for custom memory layouts for ADTs, which is the green exploding node here, which we add onto the traditional compilation pipeline in black. So what happens is that the user specifies an intricate representation once and uses high-level data types and manipulation code, that is ADTs and pattern matching, which remain the same as with a naive representation. We also provide formal criteria that define agreements between memory layouts and ADTs. And we also provide a new pattern matching compilation algorithm, which is capable of emitting low-level code that actually knows how to deal with data represented in whatever twisted way we specified earlier with the memory type. So this is all implemented in our compiler, which is called Ribbit, and again, a web demo is available here. So we're first going to look at the memory layout specification part, which consists of a specification language, some DSL, as well as formal agreement criteria between nice high-level types and clever custom memory layouts. We're going to use this example to represent our DSL. This is basically what Linux-style red-black trees will look like if we only deal with immutable data. So we're going to use a single bit for the color, 0 for red and 1 for black. Empty is going to be a 64-bit wide word with its lowest bit set to 1 and then unspecified padding for the rest of the word. And when it comes to node, it's going to be a 64-bit wide pointer with its lowest bit set to 0, its second lowest bit used to store color, and it's going to point to a structure, a struct with 3 fields. So the 64-bit wide integer left and right subtrays at the end of the pointer. So we're going to see how to express this layout in Ribbit in our DSL. First going to see how to specify a very simple type, which is color. So in Ribbit, every custom type consists of first a source type, which is a standard ADT. Here color is the same as before. Then we get the keyword represented as, and then we get the actual layout specification, which is called a memory type. The only information we have to encode for the color is a tag, which is red or black. And whenever we want to specify different representations for different tags, we're going to use a memory type construct, which we call a split. So splits are kind of similar to dependent types in that they express that the precise type, precise shape of the value we're dealing with depends on some part of it, on some discriminant value. Here we have 2 split branches, 1 per tag. Each branch consists of a discriminant value, 0 for red, 1 for black. It's going to be the concrete value in memory that identifies the branch. We get then a provenance, which is the link between source and memory types. It indicates which tags this branch applies to. And finally, on the right-hand side, we get the specific memory type, in this case, I1 for the single bit. And so we can see that this memory type encodes the desired representation, a single bit which is set to 0 for red and 1 for black. But with such a simple type, we haven't gained much compared to C. So we're going to see what happens when we try it with a more complex type, the actual red-black trees. So the RBT type features a tag with several fields inside, which is the node tag with its 4 fields. And also we want to express a WebAffine aspect, which is bit stealing right here. Since we're dealing with an enum, a sum type, we again start with a split. But since we're not inspecting the whole memory value this time, we're going to specify a discriminant location. In this case, it will be the lowest bit in the square brackets here, which is the part of the memory value we're going to use to distinguish between the two tags, empty and node. So again, we have 2 split branches, one for each tag, which is why 1 bit is enough to distinguish them. We specify that the lowest bit is 1 for the empty tag and 0 for node, with discriminant values and provenances just like before. So in the empty case, we only need to say that the lowest bit is 1. We do so with what we call a bit-word content specification. It's introduced with the keyword with, and here we simply say that the lowest bit of the 64-bit wide word is always equal to 1, using the same location as the discriminant location to get the lowest bit here. And then after the colon, we get a single type to assert a fixed value, in this case 1, at this location. So it is redundant with the split left-hand side, which already says this, but we could leave it out and let Ribbit infer the specification, but we're just going to go with it here. And this is sufficient to encode the empty tag. The node case is a little more complex because we also need to fit 4 fields. So we first specify a 64-bit wide pointer whose 2 lowest bits are free due to address alignments, which is okay because we're going to point to a word-aligned struct, as we'll see later. Also, since we have asserted that 2 bits are free due to address alignment, we're going to specify their contents. So the lowest bit is set to 0 because it's used as the split discriminant, and the second lowest bit is going to contain a color, which fits into a single bit, and this is how we describe bit stealing. So we encode the color using a construct which is called a subterm, which are used to express that some part of the source value here should be represented there in the location we specified according to some memory type. For instance, here we say that the field C of the node tag should be encoded right here as a color using the memory type we defined earlier. So together with split provenances, subterms are really what intro memory types to the source ADT. So the struct at the end of the pointer contains 3 64-bit wide fields, which each encodes a field from the node tag above of the original type, again using subterms. So the field V is encoded in the first field on 64 bits, and left and right subtrees are recursively represented in the second and third fields. And now we can see that we covered all data from this tag from node. Finally, this memory type specifies a complete layout for the RBT type. Now, what's not immediate just from the specification is why this memory type is suitable for encoding radioactive values. So for this, we have several formal criteria, which we call agreements between source and memory types. So they're formally described in the paper, and here we're going to look at the 2 main ones informally. We have distinguishability in orange, which deals with sum types. It ensures that all tags can be told apart by inspecting 1 or more split discriminants. In our case, it's okay because we can look at the lowest bits to distinguish between empty and node. And we also have coverage in blue, which deals with product types by ensuring that all data from the source type appears in some form within the memory type. And here we can see that each of the 4 fields appear somewhere in the as a subterm. So far we have focused on types, and now we're going to look at data manipulation code. More precisely, we're going to look at how we use the memory type during pattern matching compilation to generate low-level code that deals with data that follows a custom memory layout. The syntax is unchanged, which means we must compile high-level code to layout-specific machine code. So in practice, it means compiling pattern matching to decision trees, which consist of switch nodes, the rectangles here, and leaves, which are the green nodes here. Each switch inspects some part of the memory value, and every leaf says that if during execution we reach this point, then the pattern associated with this ID is the one we match. So we're going to use this synthetic pattern matching example to illustrate the compilation process. It features 3 patterns with a little bit of nested constructors and some wildcards, and our goal is going to be to emit the following decision tree. So far we have seen the input language on the left, and now we're going to go through the computation process on the right, which consists of 3 main steps. We're first going to, a characteristic of our compilation process is that it's tree-based and it's directed by the memory type, because memory types are rich enough to capture all necessary information for pattern matching, and we're going to use this fact to refine the decision tree we're going to produce progressively. So the first step of computation approach is to build a skeleton decision tree whose structure reflects that of the memory type. So far we can see that every leaf is empty. They will be populated by patterns later on in the next step. The empty set means that no pattern currently accepts values that reach the given leaves. So we can see that every split in the memory type maps to a switch node in the decision tree that inspects its discriminant location. And there's also another type of node, which we call parallel nodes or par nodes, which group together parts of the memory type that do not depend on each other, like fields of the structs. And basically the semantics of that is we should simultaneously evaluate each subtree, and as for which pattern we match a pattern if and only if every branch says we match it. So we just captured the structure of the memory type with scaffolding in this tree. The question is now, how do we add pattern information? So we do this with a step called weaving. We weave each pattern into the tree, and its goal is to populate leaves with pattern IDs and to expand the parts of the tree that we need to inspect nested subterms. So we proceed by following the shape determined by the memory type with choices as switch nodes depending on the pattern we're currently weaving. Here we're going to start by weaving the empty pattern into the tree. Since the empty tag always sets the lowest bit to 1, we only explore the 1 branch of the root switch node, then we reach a leaf, which means there is nothing more to inspect, and so we add the pattern ID A to the leaf to say that the pattern A accepts memory values that reach this leaf. Now we're going to weave the second pattern, which only accepts node values. So again, we only consider the 0 branch of the root switch. Then we encounter 2 parallel nodes, which correspond to the pointer and structs in the memory type. So we're going to recursively explore every branch of these par nodes. And so one of these branches is a leaf. So just like the previous pattern, we add the output ID B there. And then we're going into an issue, because if we look at the leaf highlighted in green, it corresponds to the color field, but we can just add the output ID to this leaf because this pattern does not accept just any kind of color value, it only accepts black. So what we need to do is to inspect the color value itself to only match this tag. Since the leaf is annotated with a memory type, color, we're going to grow a new memory tree right there that inspects values of type color by calling scaffold again. So such annotated leaves are actually called buds because whenever we need to inspect subterms, we just grow the buds into a new tree. And so this is the result of growing the color buds. We scaffold a new tree for the memory type color, and so we get a switch on which we weave the sub-pattern, black, and this is how we get the output ID B on the leaf coming from the 1 switch branch. Moving on to the second field, the integer value. Because the sub-pattern is a wildcard, there's no need to grow the buds, and we treat it like a leaf. We add B to say that we accept any integer there. Left subtree field, again, the pattern does not accept any red black tree value, so we grow the highlighted red black tree bud. And we get a new red black tree, and since we're only interested in empty trees there, we add the pattern ID B to the leaf coming from the 1 switch branch here. Moving on to the last field, for the right subtree, we have a wildcard, so we just add the pattern ID to the leaf. And the last pattern we have to weave is just a wildcard, so since we accept any kind of red black tree value, we're just going to add the pattern ID C to every leaf and every bud in the tree, exploring every branch. And so now that every pattern has been woven into the tree, it means that all relevant information, types, patterns, has been encoded, and so we can focus on simplifying and optimizing the decision tree to make it executable. So we first discard typing information by turning buds into leaves, and also perform a few generic transformations. Here we're going to merge the equivalent branches together. All this bunch of nodes, they say C, they say the same thing, so we'll reduce them to a leaf C. This is the result. We're left with the following decision tree in which there's still one parallel node. And the goal of this step is to sequentialize or determinize parallel nodes, because so far we have left the evaluation order of these two switches, they're unspecified because they're both independent. There's no reason to prioritize one over the other. But in order to produce executable code, we have to pick a subtree to come first. And since this kind of choice is actually a well-known problem in pattern matching computation, we're going to use classic heuristics to choose which switch will be evaluated before the other. Here we'll pick the bottom switch here. And we finally get this decision tree in which we have also only kept the first pattern ID of each leaf because the first matching pattern wins. And Ribbit also outputs LLVM IR code. So going from our decision tree here to LLVM IR, we can see the CFG here. It's mostly straightforward, but there are some subtleties that are explained in the paper. And this is the end of our compilation chain. After generating LLVM IR, we can actually execute compiled pattern matching for custom memory layouts. And so we have various type and layout examples that we use to run a few benchmarks so that we could see whether Ribbit actually reflects the expected shifts in performance, memory usage when using optimized layouts. So we're going to look at the benchmark for red-black tree rebalancing, which we compiled with Ribbit for OCaml, Rust, and Linux layouts. And we also have native versions of OCaml and Rust layouts using their respective compilers. For these slides, we'll focus on two metrics: the total space taken up by sampled red-black tree in memory, so we count it in 64-bit wide words, and also average execution time of our compiled LLVM so our compiled decision tree on the same sample red-black tree. The first thing we can notice is that we find the exact same memory usage between native and Ribbit, barring a difference of one root pointer. So it's a good sign that Ribbit accurately models existing representations. Then we can see that the Linux-like layout takes up much less space, which was expected because it's specifically optimized for space. And when it comes to execution times, we have to be careful when interpreting these numbers because we're comparing different runtimes. What we're really interested in is the speed up between different layouts. And we can see that with Ribbit, we do get a wealth correlation between layout optimization and performance improvements. So this tells us two things. One is that it is worthwhile to take the time to optimize memory layouts, even though now we don't need to do it in C with structs and unions anymore. And also that Ribbit matches real-world compilers when it comes to the relative performance of different layouts. The full benchmarks are more extensive and they're available in the paper. So we've gone over some features of our input language as well as the basic steps of our computation algorithm. What is missing and what is available in the paper is the full formal agreement criteria between source and memory types. And from agreement at source level typing, which is just classic typing, we're able to prove the correctness of our computation algorithm. That is, that it emits a decision tree that's semantically equivalent to the source pattern matching. Again, the proof is in the paper. We also capture various real-world memory layouts, including the bit-stealing red-black trees we just saw. And we also have stuff like replicate-like NAND boxing, some quite brutal inlining, some struct packing, etc. One future direction is to integrate our memory types with other compilers like MLIR or even Rust, who knows. We think that users probably don't want to write all memory types by hand, so it will probably be more interesting to use them as IR, as intermediate representation. And we aim to capture as many existing memory layouts as possible. So we already have a few, but there are many, many more. And so all kinds of hand-tuned memory layouts or just weird layouts are wanted and welcome in the great wide memory type zoo. And please come and tell me about your weird memory types. So I'm going to end this talk with an example of yet another wonky memory layout. This one is for arithmetic expressions, which reclaim some padding bits to inline integers. And so thanks for listening to me. Go play with the online demo and come tell us about your weird memory layouts.
questions?
Hi, I have a couple of questions. I'll ask one.
Name and.
I'm May Milano. I'm an assistant professor at Princeton University. There are some aspects of traditional functional runtimes, like OCaml's garbage collection bit, that are already taking advantage of packing in extra information into spare space and pointers or cutting off integers a little bit early. How do your techniques interact with that? And could I represent, say, OCaml's garbage collection tricks in your techniques?
So for the representation part, I'd say most probably, yeah, definitely, because we capture quite wonky things. And as for whether our approach could interact or how it will interact with garbage collection, etc., I have not thought about it, but we're mostly thinking about people who want performance, who want performance so desperately, they're going to write custom memory layouts in C, so they probably won't be going to be using garbage collected languages. I think so. And actually, with custom shaped data, I think the GC might have trouble with that, so it's probably
That's what I
for
was
the
curious
best.
about, yeah.
Oh?
That was what I was curious about, if you knew if the language was collectible in general.
We haven't thought about it. What we currently have is a toy language with pattern matching and ADTs, and we compiled it down to LLVM, and there's no garbage collection at all.
Hi, I'm Jeremy Gibbons from Oxford. That's a very nice talk, thank you. There was also a very nice talk earlier today on fully in-place functional programming that
Yep.
was kind of related but kind of different, about reusing the memory but not doing all your clever wonky data type squishing. Have you thought about putting the two together?
So I have given it some thought, but so far we've kind of swept mutability and stuff like that under the rug. And so allocation is quite an interesting topic that high-performance programmers are also very interested in, obviously. And so this is also a future direction, I think, to think about how all of this works when we need to actually allocate data, whether we need to allocate a big chunk of space and even be done with it, or whether a particular layout will affect how we need to allocate data. It's not something we've thought too much about so far, because we assume we're just going to allocate once, build up some fixed data, and then pattern match on it. But yeah.
Okay, thank you.
Hi, I'm Richard Eisenberg from Jane Street. I had two questions, but one of them has already been asked, which was about garbage collection, so thank you for your answer there. The other was, can this be used for sort of asymptotic gains? So sometimes it's particularly convenient to essentially work with unary natural numbers, but of course that's sort of ridiculous at runtime. Is this system capable of sort of saying that, oh, instead of having this sort of unary representation, that actually we'll just use a binary representation? Can it go that far?
So like using different encodings for numerical values?
Well, I mean, it's so unary natural, right? It's like it's storing a natural number by using a linked list and just sort of treating it as its length. But
Actually, it's also kind of a future directions. It's much more general. The linearization of recursive data, in a lot of situations, we want to squash it into oblivion, into some sort of flat structure. So we can perform some quite brutal inlining, but what we can't do yet is stuff like inlining, like flattening lists, or technically struct of array and array of structs is out of bounds too. Probably the next, very next thing we're going to work on is to look at arrays and how I can flatten data.
Sure, thank you.
So I had a question about the code Sam Tobin-Hochstadt, Indiana University. I had a question about the code generation. So when you showed the LLVM IR that you were generating,
Yep.
you broke down each of those individual switches into separate LLVM IR. Of course, those first two switches are looking at bits that are next to each other. And almost certainly, if you were writing this in C code in the Linux kernel, you would look at
The whole at
the
once.
pair of bit patterns and combine things
Yep.
in some way. Now, it might be that LLVM and inst combine just knocks all of that out and does the right thing, but seems like a trust but verify sort of situation. So I'm wondering, does LLVM generate the kind of code that a low-level programmer might write instead of the naive compilation, or is that a future thing that you would have to optimize?
So I think it really depends on what kind of options you pass to the LLVM compiler. It's able to do some quite, again, brutal optimizations. This is LLVM without any optimization. We run it to keep the raw structure of the decision tree. Now, if we wanted to solve this on the memory type side, it would be completely possible to say that we split on the duo of the two lowest bits instead of having two separate splits, and to say 0 is this, 1 0 is that, and it's also completely possible to just not map a possibility if it doesn't make sense. So yeah, there are two.
I guess I'm curious what the result of LLVM optimization looks like for this, and whether it removes the need for optimization at the higher level.
So I don't have it at hand right now, but I don't remember if with O3 and like it merges these two locations. So it's a good question. I have to look at whether LLVM does that or not.
In this web thing where you can play with it, can you get to see the final machine code as well?
Sorry?
This thing that you can play with your compiler on the web.
Oh yeah.
Do you get to see the final LLVM code or machine code?
Unfortunately, that's exactly the part that's not on the web demo, but the source code is also available. So if you're determined to see the compiled output, you can check out the source code.
All right, let's thank the speaker again.